Did anyone hear what I just asked?
Yes, I have questions. We have questions.
Yeah. So what I do have is questions on sequences, which obviously will be on that test. The question number 1. Use the divergence test. Use the divergence test to determine whether the series converges or diverges. That's the first type of question. And one of the examples that you had on your homework was sum, okay, from 1 to infinity, square root of 9k squared plus 7 over k. So how do we do here? How do we use the divergence test on this problem?
Would you change the series into a function of x and then evaluate the limit?
We need to evaluate the limit of the sequence. It doesn't actually matter what variable is there. So you can take the limit with x or with k, it doesn't change anything. All right. Thank you. So here you are going to say you got ak equals square root of 9k squared plus 7 over k. Limit of ak as k goes to infinity equals limit as k goes to infinity of square root of 9k squared plus 7 over k. And you can see that everywhere here it's written limit. When you don't have this, there's no way you can get full credit because you don't have a limit equal to a function and then somehow equal to a number here without the k inside. So it's a limit equal to a limit, and to compute this limit, you still have limit as k goes to infinity. And then I said, you take the highest power of k. That's square root. Here, the highest power is 9k squared with its coefficient divided by k. There's no way you can tell me that this is 3k plus square root of 7 inside here, and then you continue taking the limit and you say it's correct. It's not correct because square root of 9k squared plus 7 is not 3k plus square root of 7. The only correct thing to do is to go out there. And now you can take square root here. That's square root of 9k squared. Limit as k goes to infinity of 3k over k. And 3k over k is 3. That's why the answer is 3. And so that limit as k goes to infinity of ak is not equal to 0. Therefore, the series diverges. That's it. There's nothing else about that. And you need to know the rule and be able to compute the limit. Two things. Know the rule, be able to compute the limit. Any questions on this? A second example of the same kind. Still under that question 1. Same kind of question. Second example. Sum k from 1 to infinity 7k to the power 6 over k factorial. You would say ak is 7k to the power 6 over k factorial. And you need to find limit as k goes to infinity of ak, which is limit as k goes to infinity 7k to the 6 over k factorial. And this problem, one of the things that you can do to find this limit is to use what you call the squeeze theorem in Calc 1. You can say that this function right here, 0, is always less than or equal to that ak, less than or equal, and k factorial, you can say this thing is 7k to the 6 over, and here you can say k times k minus 1 all the way down to k minus 6. Why? Because factorial k, as I gave you in class, was k factorial is k times k minus 1 and multiply all the way down to 2 times 1. It's the product of all numbers, all integers, all positive integers from k down to 1. So if I take that k factorial, I write it as this times that times that times this. Why do I do up to k minus 6? Because that will give me at least 7 powers of k. And this thing will be less than, because I would still have to multiply this thing by more numbers coming down. So if I multiply by more numbers, I get this. So this number here is less than that one. And now this one is easy to use, because here I'll just say this thing by the squeeze theorem is less than limit as k goes to infinity of 7k to the power 6 over k minus 1, k minus 6. And then I use the rule that we just used in the previous problem. It's a ratio of two polynomials, so the limit is nothing but the limit of the ratio of the highest powers of k. So that's k times k times k times k 7 times and k to the 6th divided by k to the 7th is 1 over k, and the limit of 1 over k, that's equal limit as k goes to infinity, and then you had the 7 over k, that's 0. So the limit of AK in this case is 0. Why? Because of the work that you've completed. So you have on this side, based on this, by the squeeze theorem, 0 less than or equal to the limit of AK and less than or equal to 0. So by the squeeze theorem, the limit of AK when K goes to infinity equals 0. And that being the case, the divergence test is inconclusive. Questions?
I've got a question. When you're doing the squeeze theorem in the denominator, why do you go to k minus 6 with 7 k's instead of going to 6 k's?
Because I need to have enough k's to cancel this, because I have the feeling already that this limit is going to be 0.
Okay.
And for that to happen, I need to have more powers down than on the top, right?
Is it always going to be one more than the top exponent?
You need at least to have something more than the top if you feel it's going to 0, because your explanation typically is what? You say that this thing goes to infinity faster than that thing, right? But if you are saying that you need to be able to find a way to measure that by showing that it has at least a power that is larger, right? Does that make sense?
Yes.
That makes sense.
So often when you have exponential, when you have powers of k and then the factorials, then you take out of the factorials enough powers to kill the effect of the power of k. It's usually one more is better. Doesn't waste too much time. Is that all? All right, so let's see what's next. And the next question is about the integral test, which is one of the most important things that you have there. That'll be question 2. Integral test. And the first example here is sum k from 4 to infinity of 1 over 7 e to the k. Use the integral test. Again, same question. Use the integral test to determine whether the series converges or diverges. And here, to answer this question, you need to check all the options, all the assumptions that we have on the questions as done in class. 1, you report that function inside there is positive. 2, you show that the function is decreasing. And 3, you give the interval where it is continuous. Before computing the integral, if you don't have that, all of that, you have at most half of the credit for the question. So to use this, you're going to say, okay, AK is 1 over 7 e to the k. This thing is positive. Then you find AK is f of k, f prime of k equals the derivative of this function is minus 1 over 7 e to the k. And this derivative is negative, which means that f is decreasing. Then the last one, you report the interval. F is continuous on that interval where you have the sum. Then, okay, you have all the assumptions that are necessary for this theorem, and now you can apply it to compute the integral. So the integral from 4 to infinity of 1 over 7 e to the x dx is nothing but 1/7 integral from 4 to infinity e to negative x dx, which is 1/7 minus e to the negative x from 4 to infinity. And then when you're checking infinity here, it's like plugging in for the limit when x goes to infinity of e to negative x. E to negative x when x goes to infinity, that's 0. Minus, and then you got minus e to negative 4, and then the 1/7. So here it's 1 over 7 e to the 4th, which is saying that the integral converges. So the series converges because the integral converges. That's how the question should be answered. Any question on this? Another example on the same topic. 2 of question 2. Sum k from 2 to infinity. 1 over k ln of k squared. Again, use the integral test. And again, you say AK is f of k, and that's 1 over k ln of k squared. This thing is positive because ln of k is positive for any k larger than 2. K is positive, so this thing is positive. And then you have f prime of k. Take the derivative of this. That's minus, because 1 over, so minus derivative of this function. Use the product rule. now be ln of k squared minus k times the derivative of ln of k squared. That's 2 ln of k over k divided by k ln of k squared. And the answer is, the k is canceled. You can factor out ln of k, so that negative ln of k times ln of k minus 2 over k ln of k squared. We can simplify this, but it's really not needed. Nobody wants you to do that. So right here, you can see ln of k minus 2. As long as k is larger than 3, this thing is do you even say k? If k is larger than e squared, which is at least 10. So if k is larger than 10, then this thing is going to be positive. Ln of k minus 2 is going to be positive. And then ln of k is positive, and the denominator is positive, and the negative sign here tells you that this is going to be negative for large k's. So that means that f is decreasing. Moreover, f is continuous on the interval from 2 to infinity. So now you compute the integral from 2 to infinity of 1 over x ln of x squared dx. And you compute this integral by substitution. So if u equals natural log of x, du is dx over x. And so here, that's dx over x, that's du. So you have integral of du over u squared. When x is equal to 2, u is natural log of 2, so you change that. When x is infinity, natural log of infinity is infinity. So that integral is equal to this. And the integral of 1 over u squared is minus 1 over u from natural log of 2 to infinity. When you plug in infinity, negative 1 over infinity is 0, minus, and then minus 1 over natural log of 2. So the answer is 1 over natural log of 2. This is convergent. Convergent because this is a finite number. If it was infinity, then we would say it is divergent. And now we conclude thus the series converges because the integral converges. And we don't say that the sum, we don't say that the series is equal to that integral. The integral is not equal to the series. Questions?
Can you go back to that step where you got du over u squared?
Mm-hmm.
How did you get that?
U substitution, ln of x is u. So that's u squared, and dx over x is du.
I appreciate it.
You're good. Anything else?
Can you go through how you found the derivative for the function?
The derivative of That is 1 over. So 1 over f, the derivative is, I'm missing something here. Okay. Negative derivative of f over f squared. That's how you take the derivative of the inverse of a function.
Okay, thank you.
Okay, and while you are doing that, the function itself is a product, so that's written as a product rule. X times ln of k squared. So it's product of two functions. We apply the product rule to get this. Is that a product? Yeah, it's a product rule, and I messed up on this one, so that's plus. Okay. That's a product rule. So you do k, derivative of k, it's 1, times the second function, plus derivative of the second function times the original, the first function. So k times derivative of this. And the derivative of ln of k squared is twice times ln of k, and the derivative of ln of k is 1 over k. So there are many things there. So right here is product rule. And before the product rule, you have this rule. Are we good?
Yeah, that makes sense. Thank you.
Yeah. So you do the product rule on this. You do this, you apply this rule, which technically comes from the how do you call that again? The quotient rule. This comes from the quotient rule. Okay. And then from the quotient rule, you get this part because it's a product of two functions, you get a product rule. And inside that product rule is actually another rule, because here you got ln of k squared. So to obtain this here, you're applying the chain rule. So those are all the rules of derivatives that you apply in one problem. Does that make sense?
Yeah, that makes sense.
So you start by quotient rule to get this. Inside that quotient rule, you have the product rule to get the sum of the two things. And then inside that one, you have the chain rule because you got ln of k squared. And the chain rule says what? That derivative of f of g is g prime times f prime of g. And that's why g prime here, that's one derivative of ln of k is 1 over k. That's why you got over k. And the derivative of the outside function, it's 2x. So that's 2 natural log of k. Are we good on this now?
Yes, thank you.
All right, any other things on this? Any other questions? It's actually good to have those questions because these same rules will show up in many problems that you have to solve, right? Repeatedly. So is Keisha with us?
Yes.
Okay.
I have a question.
Yeah.
Why
go
did
ahead.
you change that minus sign to a plus? Because in
It's a
the
plus.
quotient
It was,
room, don't you supposed to quotient rule? Don't you supposed to subtract?
that was a mistake for my own. It's not a quotient rule. The quotient rule gives us this formula with a minus because the derivative of 1 is 0. So this gets you the quotient rule, but the derivative on top there is the derivative of this one, which is a product rule. And in
Okay.
the product rule, you have a sum, right?
Yeah.
Then inside you have that chain rule. And you can see that I can have a mistake because nobody is perfect. But when you do that, you look at it and then you check back and you see, oh, this is what actually happened. This is why I was having an issue, and you correct it. It's perfectly fine. There's no problem to having a mistake. If you're failing my test, it's not because of one mistake. It will be probably because you don't follow the steps. For one mistake, I might say, okay, let me take 0.5 off here. But it's not going to be as much as you'll be able to, I mean, you'll be failing a test just because you had that one mistake there. Mistakes are common and normal because we are human beings, right? But the directions, that's where the problems are. Follow the directions. Any other questions on this? I tend to spend a lot more time here because I believe this is the most difficult thing that you have there actually. Now, on this same question with the integral test, there is a question that comes with two parts. One in which it is asking you to find the upper bound or the lower bound in something. And so let's do this. 3 sum k from 3 to infinity. We'll say 1 over, let me say even k from 1. Most important thing is not just to have numbers there. So sum k from 1 to infinity of 1 over k to the 4th. And I say, so how many terms of this series are needed to have Sn, to have S minus Sn less than 10 to the minus 5. That's one question. Another question can be find an upper bound and a lower bound for S minus S6. That's two different questions that you can be asked to answer. And these were part of the homework too. So the difference is from one question to another, all that will change is the series that you have here, but the steps in answering that question will be the same. So to answer the first question, anyway, to answer any of these questions, you need to compute the integral. Integral from n to infinity of dx over x to the power 4. You need to compute that integral because that's what the remainder is bounded by. The remainder is bounded by this integral. So whatever you do in that question, you need to compute this integral. And the integral is integral of x to minus 4 dx from n to infinity, which is negative x. When we integrate, this is minus 4 plus 1, so minus 3 over 3, right? Is that right? Then you plug it in and you plug it infinity. When you plug it infinity, that's limit as x goes to infinity of x to minus 3, that's 0. Then you plug in n, that's minus n to the minus 3 over 3. And this equals 1 over 3n cubed. So that's what we are bounded on top by. And so to answer this first question here, as to bound s minus sn by 10 to the minus 5, what you need is, so let me put here a and b. To answer a, what you need is to get 1 over 3n cubed less than 10 to minus 5. That's what the question is about. And then you solve for n. When you solve this, you get 10 to the 5th is less than 3n cubed. So you get n is larger than 10 to the 5th over 3 raised to the power 1/3. So n needs to be at least the integer part of this plus 1. So because we don't use calculators in this class, you can just write this. Which means the brackets would mean that you're taking the integer part of this number, the largest integer just before the number. And then you add 1 because you want to be strictly larger. On the setup of a test, usually what I do is I give numbers such that this thing here will not be so crazy. You could simplify this and get a beautiful n. So that's how many terms you need at least to be accurate to 10 to minus 5. And this means technically you have at least 5 correct decimal points in the estimator that you have in Sn for S. And for part B, what you need to do is use that same integral, but on both sides, 1 over 3, and on the left you will have n plus 1 less than s minus sn less than 1 over 3 times n plus 1. And because the question is about S6, that means n is 6, right? So you just plug in 6 for n. So that is 1 over 6 plus 1 cubed, that's 3 times 7 cubed is less than s minus sn less than 1. This is cube as well, over 3. This is just n on the right, it's just n cubed, 3 times 6 cubed. And this comes from what we had in a lecture, that integral from n plus 1 to infinity f of x dx is less than Rn less than integral from n to infinity f of x dx. We had a few exercises on that. So this is what is being used in that question. the integral from n plus 1 to infinity of f of x is less than Rn, less than integral from n to infinity. Let me zoom in on this. All right, that's what I'm explaining, right? Integral from n plus 1 to infinity f of x dx less than Rn, less than integral from n to infinity of f of x dx. That's what you do here, and that's why it's important to compute this integral, and then you just substitute n plus 1 to get the left-hand side. That's actually what it is. So you don't need to compute that integral twice. You compute it one time, and for the left-hand side, you just replace n by n plus 1. Am I making sense here?
Yes.
Yeah. So that's it. You replace here, and this is Rn actually. That's why you can, in a question, you could see either this or Rn. And so this is 3 times n plus 1 cubed. This is 3 times n cubed, nothing else here. And then when you plug in the numbers, that's what you get. This is cube also as well at the end here. That's it. And that's it on the topic of the integral test. Is there any question? So we have reviewed the limits, the divergence test, and the integral test. So now we still have a ratio test and a root test. And the p-series, which is the easiest one, I think. P-series and telescoping series. Now let me zoom out to continue. If there's no more question, let's go. So the questions on p-series and often of this kind, just say that's question 3. The questions on p-series are often of this kind. Just determine the convergence or divergence of the series. Okay, so when you see a question like this, in which you don't see a method that is written, please carefully listen. When you have a problem like this where you don't have a method, you need to understand that it should be one of the standard series that we use in class. 2 things are possible, p-series or who gets the second one?
Is it geometric?
Geometric series, good. So those one of the 2. If you have a question like that, it's one of the 2, p-series or geometric series. And there is no extra work that you need to do there. You just need to say, this is p-series with p equal this, and you conclude. This is geometric series with r equal that, and you conclude. No wasting time. So questions like that, that is, again, geometric series or p-series. And of course, I am talking of the setup of this, for the setup of this class, of the questions that I ask you. Not saying in general, you see something like that, it's going to always be this. But because for any other thing, I will tell you clearly, use this method to answer the question. But for p-series and geometric series, I will just ask, determine the convergence or divergence of the series. That's it. And then it'll be up to you to remember which of them is what. So first on this is sum, okay, from 2 to infinity, 1 over k minus 1 cubed. When you look at that, you see, oh, okay, what I can do here is say, I can replace n equals k minus 1. And I'm going to have sum n from 1 to infinity, n from 1, why? Because when k is 2, k minus 1 is 1. 1 over n cubed. Oh, okay. So this is P series. P equals 3, larger than 1, implies converges. That's it. Let me even zoom in. Questions?
So why did you change your n to 1?
When k is 2, k minus 1 is 1, because n is k minus 1. And I do that because this is the formula of the P series. In the P series, there is no minus 1 anywhere. So you're changing this to fit the P series. This is the definition of P series. So we make the transformation to show that this thing is actually a P series. Does that make sense?
It does.
Okay. And that's the reason why we move from k to n, replacing k by k by n plus 1 or n by k minus 1 here. So k minus 1 is n, so we replace. And then when k is 2, that's the beginning here. You replace n 2. So 2 minus 1, that's 1. That's why you get this. All right?
So if that k was a 5, would the n be 4 on the P series? Yeah. Okay.
Yeah. Thank you. And so that's the first example, and that's how it will work out. Any other question on this one? And the example would just be straightforward. No need to manipulate anything. So like this one, sum n from 1 to infinity, 1 over square root of n. Okay. This is P series. P equal 1/2 less than 1 diverges. Full stop. And you do need to tell me this. This is P series and P is this less than 1. That's the work for it. You don't just write diverges, because that answer doesn't tell me if you know what you're talking about. That's like playing a 50-50 chance. You have two words, diverges or converges. You pick your own randomly. How do I know? You need to show work, right? Now, let's say I give you another one like this one. Sum k from 5, 1 over k to the power 7. What would you say? Hello?
Would you say that this one is also a P series and that it converges because P is greater than 1?
What is P? Give me the value of P.
7.
That's it. You need to write that. P equals 7. So this is P series. And the way I know you know it's a P series, you give me the value of P. That's P equals 7 in this case. And that is larger than 1. This right thing to me that it's larger than 1 tells me that you know the rule. That's why there is credit for that. You don't have that, you lose credit. Giving me P shows that you know what P series is. Telling me that P is larger than 1 tells me you know the rule. And then you conclude from that rule, converges. Questions?
Does the fact that the series starts from 5 change it at all, or is that?
Doesn't matter. There is another question in which we will show that if the sum converges, then if you go forward by 5 terms and start, it still converges. So if you drop the first terms, it still converges. Right? So it doesn't have to start at 1 here. Any other question? Eric? Sydney? Are we together?
Yeah, I don't have any questions.
Okay. Jace?
I'm good on these.
All right. Now the next one will be an example that has to do with geometric series. So sum k from 0 to infinity, and then 3/5 0.3 to the k plus 3/4 times 0.5 to the power k. So, and the way we answer such a question is we think of it as the sum of two converging series. And one of the rules that I gave you was that if we have two converging series, then their sum converges. So this thing, if the question is find the sum, then it is telling you already that it converges, so you don't need to worry yourself showing that it's convergent. Find the sum, then you find separately. So this is sum k from 0 to infinity, answer 3/5 0.3 to the power k plus sum k from 0 to infinity 3/4 0.5 raised to the power k. And this is equal to this first one, that's geometric. R is 0.3, A is 3/5, and the answer is A over 1 minus R. Because the sum starts at 0. You be very careful with the place where you start your sum. When the sum starts at 0 here, and it's power k, then the sum of a geometric series is A over 1 minus R. So the formula that is used here is that formula. A over 1 minus R. For this one, A is 3/5 over 1 minus R is 0.3. Plus, for this one, this is also geometric. A is 3/4, that's it. R is 0.5, that's right there. And so this is the A of this one, that's 3/4 over 1 minus the R of this one. That's it. And so if you want to do the algebra, you can do it, but I really don't need it. So that would be 3/5 over 1 minus 0.3 is 0.7, and 0.7 is 7/10 plus 3/4 over 1 minus 0.5, which is 0.5, which is nothing but 1/2. And when you are dividing a fraction by another fraction, you multiply by the inverse of the bottom. 5 cancels, so you get 6/7 plus, and here 3/2. That'll be 12 plus 21. $33, I guess. Over 14. So that's what that sum is equal to. And this reviews for you the geometric series and how you add them. Question.
Wait, where did you get 33 from again?
You're adding 6 sevens plus 3 halves.
So
Right.
how does the term that the series starts at affect the geometric series?
If it doesn't start at 0, you have to bring it back to 0, either by adding terms or taking off some powers of the number you have here. Otherwise, the sum is not equal to that. The sum is equal to a over 1 minus r. When you have that formula, sum, okay, from 0 to infinity of a r to the power k. For this sum that you have that, when it doesn't start here, you need to get it to this form. If it starts at 5, you need to do the translation the way we did in this previous problem. As we did translation in this problem, you can do translation if it starts at 5. You can replace k by k minus 5 to make sure it starts by 0. It's a good question. So let me put right away an example of what I'm talking about. That will be better seen. If you say you have sum k from 5 to infinity of 3 times 1/5 to the power k. For this sum, you need to see that you need to do the transformation to get this number to start at 0. So you replace k minus 5 to make sure you start at 0. So that's going to be sum n from 0, because when k is 5, n is 5 minus 5, 0 to infinity. And now 3, and then 1/5 to the power k, and k is n plus 5. Because n is k minus 5, k is n plus 5. And now you see that it starts at 0, but the top power is not n, right? If it's n here, you got to have n there. You got n, 0, good, but the power is not n. So you got to remove the extra powers from here. So that is going to be sum n from 0 to infinity, 3, 1/5 to the power 5 times 1/5 to the power n. Now, this is n equals 0 sum powers of n, so that is r, and this whole thing that came out is a. Do you see this?
Yeah, that makes sense.
So now this is the new a. Though you would think at the beginning that a is 3, actually for this one, a is 3 times 1/5 to the 5th. So it's very important to know where you're starting for the geometric series. And therefore, and this sum is nothing but a, which is 3, 1/5 to the 5th, over 1 minus r, 1 minus 1/5. Okay. Any other questions?
So, would you want us to simplify that or keep it like that?
Like that, I'm fine. You're not supposed to use calculators, so If you're trying to do that and you mess up your answer, you're losing points for no reason.
Is it the same thing for the first one you did before that?
Yeah.
Okay.
Thank you. And so now there's one thing you need to do with the alternating series. It's question 4. It's, if you're following the way I'm writing this down, you can understand that we already have 4 different sets of questions, right? So that alternating series, that would be 4 type of question. And then you have root test, another type, ratio test, another type, that's like 6. And then you have question on limit of sequences, that's 7. So you have around 10 questions. So for alternating series, let me get the example here. Sum n from 1 to infinity, 16 over 4n minus 3 times 4n plus 1. Okay. No, but usually, actually, when I ask this question, I make sure I already put it in the form that you don't need to do the partial fractions here to get it, okay? So this is, let's say 16 over 4n minus 3 times 4n plus 1. We want this to be a over 4n minus 3 plus b over 4n plus 3. So we cross multiply and get rid of the denominator. You get a times 4n plus 3 plus b times 4n minus 3 equals 16. And so we identify the terms. You get, on the left, you have 4a plus 4b times n. On the right, there is no n, so this is 0, which tells you that a equal minus b. Then you look at the constants, you have 3a minus, what's that, plus 3? This is plus 1, right? I don't know why I got plus 3 there. That's plus 1. So that's a minus 3b. So a times 1 plus minus 3 times b. And that's the constant. And the constant on the right is 16. We are doing here what you call partial fractions, all right, when you were doing integration. So this is a, and then I replace b by minus a, so that's minus a plus 3, a equals 16. So 4a is 16, so a is 4. And then b is minus a, so b is minus 4. So we got the a and b. Now, the most important thing about this question is what follows after that. So we have a 4, so that's 4 over 4n minus 3 minus 4 over 4n plus 1. And then we have sum n from 1 to infinity of this. And in class, the first day we work on this, I say you come here and you identify this as an. This part, you take it as an equals 4 over 4n minus 3. And then you find an plus 1 plug in n plus 1 here for n and see what you get. That's 4 over 4 times n plus 1 minus 3. And this is 4 over 4n plus 4 minus 3 is plus 1. So you can see that computing an plus 1 gives you exactly what you have here. So this thing is sum n from 1 to infinity an minus an plus 1. That's why it is telescoping series. And to answer the question, I say you have 2 steps. Write down Sn first, then find limit of Sn. Anything else is wrong. So you get Sn equals first term, that will be A1 minus, when you plug in n equal 1, that's A1 minus A2. That's the first term, plus second term, that becomes A2 minus A3. Plus third term, you can see it's going to be A3 minus A4. And then it will continue, and the n term will be an minus an plus 1 as written in the formula. That will be the an. 3, 2, 1. And now you can see that things cancel. That's A2 cancels A2. A3 cancels A3. A4 probably cancels the next one, and the an here cancels the previous one. So you're left with A1 minus an plus 1. And please watch the video also of the lecture that we had on this. This same formula is derived there, and you can do that. So you can see that in the end, Sn in this problem is A1. What is A1? Plug in n equal 1. So that's 4 over 4 minus 3 equals 4. So that's A1, which means that Sn is 4 minus 4 over 4n minus 3. That's Sn. That's the first step of answering this question. And then you go to the second step and you find limit as n goes to infinity of Sn. And that is limit as n goes to infinity of 4 minus 4 over 4n minus 3. Now you plug in n. 4 over infinity is 0. 4 minus 0 is 4. So that's it. And that's why you would say that the series, the sum of the series, is 4. 2 steps. Any questions?
Could you go to the bottom of the last page for a minute? Okay, thank you.
Welcome. Okay, so that's it. That's how it ends on this one. So the next thing is a ratio test. Question 5. Use the ratio test. First thing here, sum k from 1 to infinity, 7 to the power k over k to the power 750. Technically, when they put these things here, and you see 7 to the power 750, you know that it should be something stupid that is not going to play any major role. So you got AK is 7 to the k over k to the 750. And then you write ak plus 1. That's 7 to the power k plus 1 over k plus 1 to the power 750. And then you do a k plus 1 over ak. That's 7 to the k plus 1 over k plus 1 to the 750 divided by 7 to the power k over k to the power 750. 7 to the power k plus 1 divided by 7 to the power k, you have a 7 that remains there. Then you have this, which is a denominator, it goes to the top, it becomes k. You can put them together actually, k over k plus 1 to the power 750. And so when you find a limit as k goes to infinity of ak plus 1 over ak, you get limit as k goes to infinity. And when you do simplify things like this before finding limits, you see clearly what you're doing. Otherwise, you're trying to trick yourself because you cannot trick me. So now you have 7, and then you have k over k plus 1 to the power 750. Now, finding this limit, this is a ratio of polynomials. K over k is 1. 1 to the power 750 is 1. 7 times 1 is 7. So this limit is 7. And it is larger than 1. And because we are doing the root test, that means that the series diverges. Questions? We got one last thing left, which is the root test. And here I say sum n from 1 to infinity 2k plus 7 over 9k raised to the power k. And I said, when you see something like this, you understand that even if we don't tell you it's root test, you understand it's going to be root test because everything is raised to the power k. So ak is 2k plus 7 over 9k raised to the power k. So we find the kth root of ak is going to be 2k plus 7 over 9k. And we take limit as k goes to infinity of the kth root of ak. And that's the limit as k goes to infinity of 2k plus 7 over 9k. And this is a ratio of polynomials again, so that's going to be 2k over 9k, 2 9s. And this limit is less than 1, which shows that you understand the rule that you're working with, and that implies that the series converges. And for that, the time is over. So I would ask you to Watch the video on limits for this. I need you to follow all the steps that are done there, not just tell me that the answer is e to the 3. I know that. But when the question says find, that means you need to go through all the steps, take natural log, find the limit, and get the e to the a. That's it. We are like 6 minutes already over time. So that's why I can't continue down to that. Any other questions before we go?